Right. All right. So greetings, everyone. I'm here to talk about garbage collectors, and I suppose I'll be explaining this more later, but um, I'm comparing garbage collectors in three different languages. But I think that most of this, the whole motivation why we ever got started into this discussion, why I prepared this material, is because of Julia, and because I think that people are starting to look at Julia and Julia as a high performance language, but then there's that, oh, but it has a garbage collector. How could it possibly be a high performance language if it's got a garbage collector? And so I think so I did some investigations and for and it's really being, I'm putting it out there for people to draw their own conclusions about it, but I have some opinions of my own, and I'll share them when they come up. So first, let me say that I'm taking a step back in a big picture, that programming languages can have or cannot have, depending on the language, various dynamic features. There's a number of things that could all be called dynamic, and by dynamic, they are features that the language lets you think about things in a sort of more cloudy way than a hard, bare metal kind of way. Quite a few of them. Garbage collectors is just one of them. One that I like to emphasize, because we kind of don't even think about it anymore, we automatically, of course, take it, is dynamic memory allocation, just the ability to malloc and free. But then there's also metaprogramming features where can you eval a string that you create at runtime? Can you JIT compile it? Dynamic instruction set, this is virtual machines, and that has some utility. And of course, each one of these, actually, every single one of these dynamic things has a performance cost depending on how you use it. Dynamic data types, this is what people usually mean when they're talking about a dynamic language. And so if they're talking about Python being very, very dynamic, it's particularly in the data types. And it's also particularly what slows it down. And then I, was trying to think of, what other dynamic features are there? And I guess task scheduling is another one. Does something happen immediately as you say it, line by line through the code? Or is it something that it schedules for you? Like a famous example of this is SQL, with this whole query planner and this whole theories about query planners. And then, how do they land for a variety of languages? The first one, I really want to make the point about this malloc, or any kind of thing where you can say, please give me some memory of such and such a size, is not to be taken for granted, even though like all the languages we even think about anymore have this feature. I think Fortran 90, yes, Fortran 90 must have this feature. So I have to specify Fortran 77. Some languages that don't are things like Forth, which nobody here uses. But yeah, everything else, it's just a given that you can always allocate memory, but this is itself a dynamic feature. That's a linear search. It's just one that we've just come to accept, that performant languages can have this. And then when we're using these performant languages, sometimes we try to make sure things go on the stack instead of on the heap for performance reasons. Then garbage collection can actually be split out between the trace and garbage collections and reference counts. Both of these I'll explain more later. And then it gets kind of murkier as to what languages have them. The main difference I wanted to make is that Swift controversially took the decision that it would only have reference count for all objects, and not a garbage collector. So that only works for no cycles. Julia is a language that targets high performance and has a garbage collector. And if that at first seems odd, well, so does Go, and that's also a language that people use for performance. And then the very high level languages that they're less performant. Eval, not everything has it built in. Only a few of these are virtual machines. This one is very clear cut. Whether languages have dynamic types or even the ability to reflect types, that gets pretty murky, because even C++ has vtables for if you have a a pointer to a superclass, and you don't know which subclass it is. And then it gets very murky trying to say whether they have dynamic scheduling. So maybe I shouldn't have included that as a item. But so yeah, this talk will focus on Java, Python, and Julia. Java, not because we use it for high performance. We really don't in high energy physics. But when you think Java, well, when I think garbage collectors, I think of Java. It's sort of the prototypical example of a language with garbage collection, and a lot of focus has been spent on the garbage collection, including myself in a previous job. It was garbage collection can be very good and very bad. Python, this is a language we use a lot, and it's very dynamic in a lot of different dynamic features. It's the fact that as a garbage collector goes without saying. Of course it does. And so we usually don't even investigate the garbage collector. And that's not what if Python didn't have a garbage collector, it would still be slow. But then Julia is this up-and-coming language. It could potentially be ideal for HEP because of the way that it combines ease of use with, easy to quickly get started just scratching out some idea like prototyping. But then you can fix it up and fix it up and fix it up. Fix up your program until it's high performance. So it just seems like, it first struck me as this odd combination that, it's a JIT compiled thing, so it's very bare metal, you run things fast, but it has a garbage collector. So that's why I want to investigate this. So now let's do a short aside on Julia. Like when I'm saying it's sort of up and coming, like to what degree is it? I did a little bit of analysis on this. If you've seen before, my analyses of what physicists are using based on looking at GitHub. Well, here's one that's targeting languages in a very generic way. So I first selected a group of GitHub users using their bios. This is I used to use did they fork CMSSW in order to find CMS users. And then I tried other things like have they ever interacted with the root repo? And those don't always find exactly physicists because they're people who, yeah. This technique is selecting people by their bios, and if their bio contains the phrase particle physics or high energy physics, so it'd be physicist or physics, So they're specifically saying it in their bios. Unfortunately, very few users actually fill out their bios, something like 10% fill out their bios. And using these criteria, if I were to apply it to the CMSSW set, I would have found 20% of them. So that's a good correlation. But at least we know that these are people talking about high energy physics. And then we look at the other words in their bios, and they say things like grad, postdoctoral, PhD, CERN theory or theorist, postdoc, Atlas, CMS. These are common words associated with it. We're really finding physicists. Okay, so once we selected that group, then we look at what repos they create themselves, non-fork repos. And then we look in those and ask which fraction of users created at least one file with a certain language suffix. In doing that, we find that some 90% of these people have created a Python file at some point. And here I'm not distinguishing between Python being used as driving CMSS, CMSSW or other experimental frameworks, or just doing Python. I split those out in a different analysis. A lot of them are doing shell, bash type things. A lot of them are doing either C or C++ or CUDA. Those are hard to distinguish from each other. Quite a few are doing HTML and JavaScript. That kind of surprised me. LaTeX, that's obvious. And then you're falling down into the less and less used languages. And the point is that, looking at this unbiased way, a rather small fraction of physicists are using Julia right now. It's somewhere between Rust and Lua, which are also not very physicist languages. On the other hand, people are talking about Julia quite a lot. So I went into CERN's Indico search, and over a recent time period from January 22 to November 23, there were 63 references in the materials to Julia, the programming language. And by hand, I excluded all of the references to people named Julia. This is considerably more than the two neighboring languages in the previous plot, Rust and Lua, where 63 goes down to 12 people referring to Rust, and 7 of those are in the same documents talking about Julia. They're just talking about various other languages. And Rust had to be distinguished from the oxidized metal. And then only one person is actually referring to Lua, the programming language, and is driving some program. So really, while not a lot of physicists are using Julia yet, there's a lot of discussion about it. There's discussion at ACAT and CHEP. Also, a fairly large number of talk titles compared to, other languages except for C++ and Python and Java, to mention Java. There's a HSF working group on Julia. So this is a thing that this could be in our future. Okay, back to garbage collectors. So to talk about garbage collectors, I should first explain some of the terms. I'm distinguishing between reference counting and other garbage collectors, the tracing garbage collectors, which are almost all mark and sweep. So reference counting is for each object that gets created. There's a counter, keeps track of how many references there are to it. You can do this in Python, like if you make an object called X, and then you ask sys.getRefCount. It will tell you 2, because there's X, that's one reference, and then it's also an argument to this function. And while it's an argument to that function, there's another reference. If you assign Y to X, now there's 3 reference counts. If you put it in a list 5 times, now there's 8 reference counts. And if you delete some of these references, you can get back down to 2. Sys.getRefCount will never return a value smaller than 2, because you have to have had the thing. Actually, no, it could return 1 if you construct something that's not a named variable and pass it as an argument. So basic idea is that it keeps track of the number of references, and if the number ever goes to 0, it can definitely safely delete that object, because nobody can possibly refer to it, so it can never be used again. The problem with reference counting is that this doesn't catch all the cases of when something is inaccessible. So let's say that you make X is an instance of some class that has a destructor, and I'm using the destructor just to keep track of, just to know when it gets actually deleted. If we say delete X, the reference count went down to 0, it gets deleted, and the destructor gets called. We set Y to has a destructor, and then put a variable on Y that is pointing to itself. So now Y has an attribute that points to itself. We delete it, and we do not see the destructor message. So all the references to Y are gone. It can't be accessed anymore, but it hasn't been deleted because its reference count is 1. Its self-reference is adding to its reference count. So its reference count cannot reach 0, and there's nothing we can do to get its reference count down to 0. If this was all we had for garbage collection, this would be a memory leak. But it's not all we have. In Python, you can, the garbage collector runs periodically, and you can run it yourself. And when you do so, then it goes away. So now it's gone. Most of these most of these garbage collectors, these tracing garbage collectors, use a mark and sweep algorithm. And so I'll just describe that to give a sense of what's going on, how it's able to get rid of these things that are whose only references are self-references. And that might be like a long chain of self-references. So there's some root, which is like in Python __ main __, some namespace. And so from there, you can follow all, you can just walk through this graph of what is referring to what in order to find all the things that are still alive. And whatever you haven't found that way is not still alive and can be safely deleted. And so that's how it goes. All right. So another thing is, well, first of all, this is an expensive algorithm because it has to go and look at all the objects that exist. And so some ways of mitigating that is to reduce the scope of the mark and sweep, reduce the scope of what it has to check. And it does this using generations, because in a normal program, there will be a steeply falling distribution, a large number of objects that are created and then they go out of scope very quickly, and a long tail of things that stick around for a long time. So some things go away in microseconds, other things go away in hours. And this is discretized into different spaces. And I think that, so this is Java's generations: Eden, Survivor Space 0, Survivor Space 1, and Tenured. It has these weird names, probably because garbage collectors were being developed while they were developing Java. So you got this weird thing where somehow tenure is the opposite of paradise, and I always thought that was kind of weird. But when objects are first created, they go into the Eden space, the first generation, and then this space gets marked and swept frequently. And anything that survives a mark and sweep gets moved into the next space. This happens less frequently, and so on and so on. So here's an example using Python. Python has 3 generations. They don't have interesting names. But we can ask the GC module to show us what objects are in each one of these spaces and count them. So we start by just let's get it clean. So we run the garbage collector, and then we're going to turn it off so that it only runs when we ask it to. And then tell me how many objects are there in the first space, the second space, and the third space. There's only a couple there because we just did garbage collection, and there's a fairly large number of permanent, long-lived objects. Now let's do something complicated like importing uproot. I know that's complicated. It creates lots of objects, and many of them have cycles. It is just, now we brought in a whole lot of, 57,000, a whole lot of first generation things, and we haven't changed the third generation all that much. Then when we deliberately call garbage collection, some of those things go into the third generation, and some of them are simply deleted. So we can say 57,000 goes down to 31,000. Then we do something else complicated, like use uproot to read some arrays, and that goes through a lot of code. And now we've again, gotten a lot more objects into the first generation space. But the third hasn't changed much. We clean it again, and out it goes. I think when you call gc.collect, I think this might do it on all generations, which is why the middle generation never gets, we never see it above 0. But in the normal course of things, it would go above 0. All right, so now I'm going to talk about Java, Python, and Julia. And so for all of those generalities that I've just described, the things that all mainstream garbage collectors have in common, now I'm going to talk about the peculiarities of each of these languages. And these links are helpful if you want to find out more. So Java really takes hold of the memory. It really it's a very managed space. So when you create a new object in Java, it doesn't call malloc. There are pre-allocated memory pools that Java makes these pools using malloc, and then it doles out the space within the pools to the new objects. each pool represents a different generation. So the objects that survive mark and sweep are copied from one pool into the next pool. So, it's a new, it's got a new pointer. And so there are no stable pointers. If you have a pointer to something, you never know, to some object, you never know if that pointer is going to stay good. Doing this copying, one of the benefit is that it keeps the memory unfragmented, because by copying a bunch of fragmented things that have gaps and spaces between them, like this Eden space here, by copying them into the survivor space, now they're all right next to each other, and finding new space is faster. So the linear search is less expensive. But this makes it quite difficult to use C and C++ extensions in Java. If you can never point to an object, and you can never share a pointer to an object with C or C++. Python, as we've seen, it relies on reference counting for most of its memory management. When it does the full garbage collection, it's doing it with a smaller set of objects, and that's for performance. PyPy, a different implementation from CPython, only has the full garbage collection. We'll see how that's different. The three generations, instead of copying things to different pools, the three generations are different doubly linked lists. So it keeps the object where it is. And if it's moved from one generation to the next, it'll be removed from one linked list and put into another linked list. So the Python objects, which a PyObject star points here, the first thing is its reference count, and then pointer to its type, and then other Python object stuff. The garbage collector linked lists are right before that. So these are changing all the, whenever it moves to a new generation. So the objects, they have stable pointers, and that makes them good for C and C++ extensions. But they might or might not be managed by malloc depending on some environment variables. So that gets complicated. Now, Julia is again different. The small objects, smaller than 2 kilobytes, they're managed in pools. And those pools are allocated by page. So it takes a page from the operating system when it needs it, and then it can return the page to the operating system when there are no objects left in it. And if you have any large objects, they are just use malloc. Objects have headers for type reflection, because it's, it might need to, it might have some object and need to know how to compile some new function that it hasn't seen before, based on what objects are being passed to it. So type reflectivity is essential for this language. So in that header, the first 2 bits are used for mark and sweep, mark and a generation respectively. So since there's 1 bit for generations, it's 2 generations. So this is what it looks like. The marking pass is depth first and parallel. The sweeping is serial. And so it does show up if you see all of your cores go down to 1 core. That's the sweeping part of a garbage collector pass. Memory is returned to this operating system on a per page basis, and it uses madvise, and it gets deep. If you read these things, it gets deep into the reasons for that. And Julia makes this stack versus heap user visible to help users avoid garbage collection. Since the Julia community has such a focus on performance, they make this not a hidden language feature, but something that's very much in the open. And if someone is writing on Stack Overflow some code that is unnecessarily allocating things on the heap, people will jump in and say, oh, you can change your code so that it doesn't, so that it allocates things on the stack instead. Okay, so now the rest of this talk, I'll be doing some experiments on garbage collectors, to get a sense of how they are. I mean, I think this is a good thing. Just like in physics, we do studies in order to get physical intuition. When we are using computers and relying on them quite a bit, I think it's great to do experiments on the computer to get at least order of magnitude senses of how big things are and how things, what they depend on, what variables they depend on. So first I'll do some timing experiments, and then I'll talk about memory footprint experiments, just two experiments here. And I'm doing this by creating objects. I'll just be creating objects in an array, and I can fill in the array in such a way that that I can control how long of a lifespan the objects have. The objects in question, they're all empty lists. In Python, they're empty lists. In Java and Julia, they'll be empty arrays. And I'm filling them in so I'm using these positions that have been pre-shuffled, and I'll be using the same positions in all three languages. The reason that I'm doing it this way is that, see, if I am following these for loops, for IA and shuffle B, A, for IB and shuffle B, and then fill in a spot in the array, which is these non-overlapping spots, but they're really going to be jumping around. If I follow this for IE and shuffle E with another for IE and shuffle E, then the objects I'll be replacing will have a lifespan of 16 steps. When I'm replacing an object, I'm deleting something that was created just 16 steps ago, 16 plus or minus 0. And then I can make some small changes to the for loop structure like this in order to increase the number of steps between when I'm filling stuff in. Oh, cool. Right. And then also you notice that these are all plus or minus 0. I can change the order of these. So these go A, B, C, D, E. If I go ED, EDC, or EDB, or EDA, EDCBA, go backward, then I can add a spread to this. So this was the plan. Turns out the most interesting things don't require so much care. The lifespan is a visible effect, but it's not the most striking effect that I eventually found. Then I can do the same thing in Julia. This is just what the Julia code looks like. And I can do the same thing on the JVM. And for my own sanity, I didn't actually write Java code. I wrote Scala code because you can run that like a script. But it compiles to Java, and if you look at the disassembled Java, this looks like what for loops in Java would have looked like. And these array objects in Scala really are Java arrays. Okay, so now I can do this in 3 languages, and I want to measure time, but I want to measure time the same way. So I have a separate time measuring program. That's a C++ program that listens to a socket in each of these languages every large number of steps. It will send a byte over the socket, an unbuffered socket on localhost, which in other experiments I've concluded that's pretty quick. And it'll measure the time. It'll write down when did it get that tick. So this is kind of like a sampling profiler, but instead of sampling at fixed times, instead of sampling where you are in the program at fixed times, I'm sampling what time is it at fixed points in the program. And so what I'm looking for here is a giant pause, because when the garbage collector comes in, we see a pause. All right, doing this with Java, and then I turned on the original serial garbage collector, the simplest garbage collector that it has. You can, in Java, there are all these command line arguments where you can set these things directly. I did a numerical array, so there's no objects. That's my baseline, because I always want to do experimental control. And then mutable objects. Those are those empty arrays. And we see that it usually is the same time whether we're filling a numerical array or filling an array of objects. But every now and then, there's orders of magnitude more time between ticks, and that's because a garbage collection has happened. The serial garbage collector is not the normal one. The normal garbage collector that you get out of the box is multi-threaded. And out of the box for me was Java 1.8, which is old, but that was my system Java. You can see here that it is doing, if I jump between the serial and the default garbage collector, the default garbage collector is threaded. And so it's doing something at all times and occasionally does an expensive thing. And then because Java 1.8 is quite old, why is this taking a while to go back? Okay, is this still blurry for, of course it would be.
Yeah, it's blurry for us as well.
Yeah. Preview. What's the matter with you, Preview? Should I switch to Firefox? Oh, there we go. No, it's just being very slow. Okay. All right. Who knows how Preview is implemented? Maybe there's a garbage collector.
Maybe the garbage collector was running.
Yeah, yeah. I don't think Objective-C has, well, I don't know. Whatever they're using. All right, so Java 21, I went out of my way to install this. And it has smaller pauses. Kind of afraid to jump back and forth between slides now. But it has smaller long pauses and more of these short pauses. The fact that this goes all the way down to 0, I find that suggestive of some buffering. Now look at that. Got a pinwheel. This is, of course, going to happen in a talk about garbage collectors. Okay, I think I'm going to stop. I'm going to stop with preview, and I'm going to go to something that I understand better. I'm going to do it in the browser.
Well, in such cases, you should just say that, well, you're compiling 2 other projects at the same time. That's what's slowing things down.
Yeah. Am I looking at the right one?
It's
my screen sharing is paused. Resume share. What is happening? Yeah, I think that all that pause was me trying to quit preview. So are we? Yes, we are. Good. Full screen. Should stick with what I know. Preview and Mac things are not things that I'm very familiar with. See how much quicker that is to just jump between these slides. Okay, fine. Yeah, Java 1.8, Java 21. And in Java 21, there are more options for different garbage collectors. A very recent one is called the Z garbage collector, and it has a lot of fanfare. You can see that it does more stuff at normal times, but it says fewer of these pauses. And then with the Shenandoah, as far as I can tell, the garbage collector Z is an Oracle thing, and Shenandoah is a Red Hat thing. Shenandoah during this period didn't even have any pauses. I'm not sure if it would. I'm not sure if it would if I keep going. Although it does take more time, at quiescent time. So we're trading latency for bandwidth, or the other way around. So these JDK implementations, they come with many algorithms, and they are all for different purposes. In addition to this, they also have tuning options, which I didn't explore in this talk. So this is the thing. When you're developing a Java application, you think about what you're going to be using this for. Is it going to be a real-time system? Is it going to be, something just bulk processing? And you choose your garbage collector appropriately, and then tune it. And I've been involved in that. I was, previous job many years ago, but But it was a cute problem, I'd say. It was a distributed system, and one service was sending messages to another service, and all of these things worked well in isolation. But then in garbage collector pauses, the recipient's input queue would overflow. And that created, it would just get very large with a large backlog of things in the input queue. And those things in the input queue were objects that needed to be garbage collected. So this is like a dynamic system kind of thing, like with strange attractors and such. So, like it would, randomly spiral out of control. And so I spent some days or weeks, I don't remember now how much time was spent on that, tuning different garbage collectors, trying to find the best ones for high throughput and low latency. And then there are obvious cases for HEP, triggers, data acquisition, data monitoring, basically any real-time system. You can even prefer worse throughput if in some of these systems, if you can ensure that the latency is less than such and such. And then, as promised, I did check the scaling with object lifespan, and actually I just found what you would expect, that for the short lifespans, you have only short garbage collector pauses where it's not, scanning everything, it's only scanning the most recent things. And then if they get longer, get more pauses. And this is with larger standard deviation. So that part of the experiment turned out to, show you what you expect, but it wasn't very interesting. I won't dwell on it. So switch languages, move to Python. So Python garbage collection is only triggered for mutable objects. And in retrospect, this kind of makes sense because the immutable object, if it's an object you can't change, then it can't have any cyclic references because you wouldn't be able to construct such a thing. Because you wouldn't be able to refer to, itself until after you've made it. And if it's immutable, then you can't do that. So I saw this distinction when I was filling the Python, the array in Python, just like I was doing with Java just a moment ago, with different kinds of things, cyclic references, these mutable objects, these empty lists that were not containing themselves. So they weren't actually cyclic. And in both cases, we see the garbage collector triggering, because even though these mutable objects don't have cyclic references, it still has to check them because they are there. It doesn't know that they don't have cyclic references. So so there's an action item for this. The solution to garbage collector pauses in Python is not just ensuring that you never use cyclic cyclic references. It could be if you do everything with immutable objects, that could solve it. And then we have the numerical array baseline. Let me go into a zoom. I'm zooming in here. So for the objects with cyclic references and the potentially cyclic references that don't actually have cyclic references, you see pauses. Some of them are long and some of them are short. And I find this structure interesting. I don't know the details of the structure. But then when we were making immutable objects, and I even made these big, I made them tuples with 100 nuns in them. So they're fairly large immutable objects, but they cost almost nothing. There's no garbage collection time spent on them at all. It's almost identical with filling a numerical array. And then I tried out PyPy. PyPy doesn't have this feature. It garbage collects everything, and this is a busy plot, so I just go to the zoom now. Cyclic references, mutable objects, and immutable objects, these tuples with 100 nuns in them. And I think the fact that it's 100 nuns is why the baseline is so high. Yeah, all of these things trigger the garbage collector except the numerical array. Julia's garbage collector does have pauses, as you can see here. Just like the Python garbage collector, you can turn it on and off. So you can turn it off and the pauses go away, the blue dotted line. Sorry, the orange dotted line there. And This is a bigger gap from just filling a numerical array, because when you're filling a numerical array, now it's compiled code. There's no, data type checking and such. So it's running like a C program filling a numerical array. So that's the reason for this larger gap between the baselines. Filling the numerical array, it does something with some regularity, but that is not the garbage collector, because when we turn off the garbage collector, it's still doing that something. And that something is on the order of a microsecond, every however many steps. We can zoom in on this. And one thing that I want to say about this, and this here I'm injecting my own opinions, is after looking at the other garbage collectors and having done a lot of performance studies in Java back in the day, Julia's performance curves are rock solid. Maybe you don't like that performance, and and you try to write programs that don't create objects quite so frequently. But man, that is a straight line, even compared to the Python ones. It at least makes it easy to reason about. And then I'm going to do the zooming, do the object lifespan. And as before, the object lifespan has the expected properties. Yeah, I won't go too deeply into that. This page is mostly for reference, so that Python and Julia do not have the wide spread of garbage collector options that Java does, but there are some things you can do with it, and these are those things. You can set thresholds, you can turn them on and off, you can run them intentionally, manually. And then the thing I want to mention about the Julia is that, we were talking about a language implementation, but there's also the Julia community, the community that surrounds this language. And the community has a very different culture than, say, the Python community. The Julia community is very fixated on performance. Whenever you talk about any algorithm, the subject of performance will come up pretty quickly. And the way that the philosophy around it is that, this heap allocation and garbage collection, they exist just like dynamic types exist in the language. And you use them when you're doing some rapid prototyping, the use case for Python and the early iterations of development. But then when you really want to, harden some algorithm, what you want to compute, you just want to do it faster. There are a lot of hooks for being able to do that, and people will help you find those hooks. These are some examples of that, but even the fact that Julia Lang itself centrally has an allocation checker, and that's one of the things you want to do, is like make sure there's no allocations in this hop loop. Second experiment on garbage collectors. This is I'm getting close to the end of time here, but this is resolving a long-standing misunderstanding on my part, and it's about this. Does garbage collection run more often if there's less memory? I've always assumed that it does, because I, learned in Java. My intuitions were trained on Java. Java manages everything about the memory. You can say exactly how much memory a process has, and it will never use more than that. And when it gets, when it knows exactly how much it's using, when it gets close to the limit, it'll trigger garbage collection, and it'll do everything it can to prevent running into that limit and crashing. Python and Julia, I'd always assumed so, but let's test it now. You can run a process. So if your process is command X, you can put it in a box and give that box a maximum amount of memory. And that process will act as though that was all the memory you had available on your whole system. I think that this technique of using systemd run is like a piece of what Docker does. Docker's sort of more wrapped around this, but this is all we need right now. This will absolutely limit the amount of memory that a process can have. And so I applied this to Julia. I ran that same process that was using a lot of memory, but replacing these objects. So collecting the garbage would get you up to a point. When you first fill the whole array, and then you've got the array filled, and you're just replacing objects in that array, indefinitely. If the total amount of memory available to you is more than the whole array, then garbage collection would save you. Garbage collection would be able to get you back, keep you from running out of memory. And so I put it in, and so this is the memory use of the process. USS is is a measurement of the amount of memory that would be returned to the operating system if it killed your process. So it's the amount of memory that is uniquely in this process and is not shared with other processes. So it's a good way to say how much memory is this process using. And ran this process in a box with loads of memory and with less and less and less and less. It just kept squeezing it down. And what you see is that the memory use has a sawtooth because it collects garbage periodically. And if you squeeze it down, it runs garbage collection more frequently. Like if you say that we only have 4 gigabytes of memory available, then it'll follow the lowest green line here and just run garbage collection so often that you never get in danger of going over this 4 gigabyte limit. If you ask for less than that and never fills up the array in the first place, well, then it dies. The thing I didn't know is Python does not do this. So here's running Python out of the box and put on different memory caps. And when it runs garbage collection, it has nothing to do with how much memory it has available. It has everything to do with those thresholds that I put in a reference slide a few slides ago. So I could increase those thresholds by a factor of 10 so that Python is running its garbage collection less frequently by a factor of 10. But still, if it has 8 gigabytes of memory available, okay, it dies there before it can do its first collection. If you have 9 available, it doesn't do anything differently. It runs right toward that cliff. And I didn't know this about Python. This is an important thing to know about a language you're using. So conclusions. Garbage collection is just one of the many dynamic programming language features, and some of them we just absolutely take for granted, and others we consider anathema for any high performance thing. Julia is an up-and-coming language, which could be ideal for HEP. Java's garbage collector is generational, compacting, scales with available memory, and has many, many options. Python's garbage collection is generational, 3. Not compacting, does not scale with available memory, and is only needed to clean up objects with reference cycles, but it has to run even though those objects don't have cycles. Julia's garbage collection is generational, 2. Not compacting, and it does scale with available memory. And here's where I'm injecting my opinion. In looking at all these performance plots, I would call this well-behaved. It just sticks to the line. It's very, it doesn't jump around much. And then finally, the Julia community considers avoiding heap collection a priority and helps users achieve it, just as they help you make sure that you're using templated types instead of dynamic types and stuff like that. So I see there's a lot of questions in chat, and there's some 10 minutes left for questions, so I'm just going to be available for that.
Yeah, thanks a lot, Jim. That was very interesting about a topic that I didn't know so much about, and now I feel that I know a lot more about it. Yeah, there's quite a lot of chit chat in the chat, but I think most of it doesn't need to be asked out loud. But I think we can open up the meeting now to other questions. So on Zoom, if you want to raise your hand, I'll give you a shout. And in the room, you raise your hand, but it's a different action, and I'll also shout to you. I can see that Attila's hand is just desperate to go up there. So Go for it.
No, I consider it already being up, but I was also waiting for people on Zoom. So just to start from sort of just a neighboring question, did I understand correctly that Julia uses additional threads for its garbage collection, its memory management? So
that is what I read.
So you well, can or can you not run a Julia application on exactly one core, or on exactly 2 cores, or something like this? Let's say then we want to run on the grid. What's the setup there?
I'll let Julia experts answer that.
I'm going to see if Tom knows the answer.
In the end, this is not the end all be all. I was just sort of curious.
Right. I mean, usually if you want to start a multi-threaded Julia process, you tell it at startup how many threads it wants. And then my assumption is that if you start it multi-threaded, then when it goes through the mark phase of garbage collection, it will use multiple threads if it has them. But I don't believe that it will spawn more threads in order to do the marking. So if you run a single threaded Julia, it'll just do the mark and sweep in single thread as well.
Would make sense. Sure.
Yeah, and as Tom's pointing out, you can set the limit as well.
And even if Julia didn't have this option, you could do systemd run or Docker. See, there's a chat.
Yeah, thanks, Tom. Okay, so any other questions or comments? Go ahead.
Sorry, I can't find my hand.
Oh, go ahead, Liz. Yeah.
Just wanted to thank Jim for this work. And my question is, do you plan to do anything with this research that you've done and presented to us here?
Oh, no, this is what I was planning to do with it.
Okay.
Yeah, we all come away with this with some more knowledge about how these garbage collectors work. This is definitely for action items for me. This changes how I'm addressing uproot bug reports. In that, how I've been. Some of them are about running out of memory, and how I've been assuming so far that Python was doing this thing with like if someone is showing that it's using more and more memory, that in the past hasn't bothered me because I was like, well, if you have the memory, it'll use it. But that's not quite right. It will, it'll use however much memory it's going to use, regardless of how large the system is. Meanwhile, if we're analyzing performance of Julia, we have to take into account the fact that when its garbage collection runs depends on the memory on the system. So we would analyze memory issues differently in Python and Julia in kind of a striking way.
Yeah. Okay, thanks.
Thanks, Liz and Jim. Charles, you have your hand up, so please go ahead. You're still muted. Okay.
I see something on chat.
Oh, you're not allowed to unmute? Can't be right.
That's curious.
Hold on.
He seems to be logged in.
Yeah.
Yeah. Curious.
Even so. Allow participants to unmute themselves. They are allowed to unmute themselves.
Oh.
That's odd.
Okay. Maybe until then, I just steal Charles's thunder, because he might be wondering about the same thing as I am. So garbage collection. Oh. Okay. That's not what I was wondering about. So Jim,
Yeah,
Question,
yeah.
have you tried C++ garbage collectors like OilPan? No. In fact, I didn't know about them. Does that introduce the, well, okay. So that's a reference for us to look up, OilPan.
So I myself was wondering, not so much about garbage collection per se, because yeah, in C++, as you said, garbage collection itself is not much of a thing. However, other things that you mentioned, memory fragmentation and even just memory caching is a thing. And I was trying to figure out during the whole talk what we could take away from everything that garbage collection does. For, I don't know, since this is the Compute Accelerator Forum, for more efficient caching of slow memory resources, these sort of things. Since you perfectly know as well, there are a number of different caching techniques for like GPU memory, and because that's a bit slow to allocate and deallocate. Anything that we can learn from all of these garbage collectors for doing this type of caching more efficiently?
Yeah, maybe not in the garbage collection, but you know, whenever thinking about garbage collection, I think about the fact that it has such a tight coupling to the memory allocator. And like, yeah, I guess I originally planned to put some content about this, but this is just a speculation on my part that I've often wondered if HEP applications could benefit from using non-standard allocators. And I don't just mean like JE-malloc and such like that. I mean allocators that use application-specific information. So one thing that, so for instance, one of the things that we know about processing, like, you know, doing reconstruction is that, at least it used to be, and I don't know if this is still current, that that the program will be concerned with one event at the time, and it'll be doing a lot of different parts for that event, all these different producers to do the tracking and the showering and such like that. But everything, all of the products that it produces for this event are only going to be relevant during the lifetime of that event. So if they are allocated on some in some memory pool, and that memory pool is just the whole pool goes away at the end of the event, instead of running through it and saying, oh, we can delete this now, we can delete that now, we can delete that now, but just like allocate them all in this one pool for event 1000. And at the end of event 1000, drop the whole pool, or just consider the whole pool fair game for event 1001. If there would be much benefit to that.
I guess good question. I personally have always shied away from trying to even write a memory allocator, because the last time I looked at it, how you would start writing something like JMalloc or any of
TC malloc.
TC
No,
malloc.
was the other
Yeah,
one.
I always quickly concluded that that's not for physicists. But yeah. But at the same time, you know that in C++ 17, we have memory resources, which make this a little bit easier. And in Atlas, we are very much going towards using memory resources in our event data model. So it might be possible to write some like handwritten allocators a bit more easily than if we were to write a full proper allocator. So
yeah. Not even handwritten allocator, but just you know, you might be able to find some off-the-shelf allocators.
There are, yeah, even the C++ standard has one that can just allocate a big blob of memory and then give out consecutive pointers into it and things like this.
Yeah.
So yeah.
Thanks, Liz.
Yeah, I was just going to comment that, you know, we have had a long history of this. Every time the luminosity bumped up from, early run 1 to late run 1 and from run 1 to run 2, we did run into memory problems. And some of it was really just the latency with which the malloc allocator handed back memory to the system. And so we did do a lot of experimentation with both, and even recently with TC malloc and J malloc and things like that, and measured their, performances in terms of when do they give it back? Do you still crash because you run out of memory? That sort of questions. And so we even oscillated recently between TC malloc and J malloc. But to go back to Jim's original point, I do agree that the event objects have a lifetime that is confined to that event, and the experiment frameworks know what the proper lifetime of that event is, even if there are multiple in flight at the same time. It doesn't matter. The higher level software still knows that. We've had to, in CMS, we've had to use some of this knowledge, and even when we had really big tracking events, have had to have the API in place to say, okay, this module promises that it is completely done with all these temporary things and is going to give it back to the EDM. So there is, some memory management while the event is in flight, even because of memory constraint problems. Yeah, and so I guess what I would say to you is that I think it just hasn't been need yet. However, I do know that Dune has such big objects in its individual events that they're struggling with this right now. And maybe something like what you're describing, where the EDM just says, okay, I'm going to make a pull for the event stuff and I'm going to delete it at the end of the event, might be good for them. But we've actually, in CMS, we've just need more finer granularity than that. Because Dune has this one big thing, that, and not lots of little things like we do with the tracks.
Yeah.
Of course, things become a bit more complicated with file I/O, but yeah, in general, one can try such a thing.
Yeah,
yeah.
I mean,
it was really just for the objects created within that process by certain modules that you knew were creating stuff.
I think in special circumstances, you could maybe see that, the way that Julia allows you to take control of the garbage collector could be useful. You can turn it off. And then at the end of having processed the event, you can say, okay, go now, when you know that it's got a lot that it's going to find that it can delete. But what performance you would get out of that, well, we don't know until we test it. We don't have, I think, Julia programs that run at that kind of scale to be able to learn useful stuff right now. Good. Well, we still have a bit of time if anybody would like to ask a final question. Jim, I'm not seeing anybody in the room, nor on Zoom. Okay, I guess that's a no then. So I think then thank you very much, Jim. It was a very interesting talk and a nice discussion as well. Who knows where we will go with this in the future, but certainly if Julia becomes more popular in the field, then paying attention to its memory performance is going to be one of the things that we have to learn how to do. So it's very useful to have this work that sort of tries to quantify what the garbage collector is up to. So great, thanks everybody for joining and for the discussion. And we'll see you in a month when we'll be talking about HEPIX benchmarking.